Section 8.4, we're going to talk about scientific notation. So the reason why scientific notation is important is that in the real world, scientists often will have to work with really big or really small numbers. So for instance, some really big numbers would be the distance from the Earth to the Sun is approximately almost 93 million miles. The distance to the next closest star, because technically the Sun is the closest star, so the next closest star is approximately 25 trillion miles away. Million, billion, trillion, yep. And then on the other side of that is really, really small numbers, like the radius of a single atom is approximately 3/10 of a meter. And so if we were to work with these numbers and need to multiply or divide or even just write them down more than once, that would be annoying because of all the zeros and digits that we have to work with. So there's kind of two answers to this problem of working with numbers that are such large in length numbers. One is to define a new unit of measure, which we've done in the past. So that's how light years are a thing, or one of the reasons why light years are a thing, besides the fact that it's kind of cool to talk about how far light travels in a year. But light years are a way that we can talk about really, really big distances with numbers that are more reasonable to work with. Like the nearest star after the Sun is actually only I think around 5 light years away compared to 25 trillion miles. I might be wrong about that, but I think that's what I read. So that's one unit that's been created to help us with this problem. Another, on the other side of that, the angstrom is actually one of the units you would find if you were to look up information about the radius of a single atom. And so that's one way to do it. The other way is scientific notation. So what scientific notation does is it takes the numbers that are at the front here, and we still have those. They'll just be written right here. And then we put times 10 to the power, and this power is basically telling us how many zeros we have. So one thing about this is that in order for us to be in proper scientific notation, this number at the front will always be between 1 and 10. In other words, it will always have one number to the left of the decimal place and all the other numbers will be to the right. So 53, even though that's a nice number to work with, and maybe even better than 5.3, that's not a number that we're not going to leave it like that. We would want it to be 5.3. So let's take a look at what we can do with scientific notation. The first thing is just getting used to rewriting it in different forms. So we have 8.76 times 10 to the third power. Well, what this is literally saying is that 10 to the third power, which is 1,000, because powers of 10 are easy because the power tells you how many zeros there are, at least a positive power does. It's saying that we just need to do 8.76 times 1,000, and that will be this number in decimal form. Because it's a power of 10, this is really easy because that just means to move your decimal to the right 3 places. So this number in decimal form, which is our normal form that we're used to, is 8,760. Whenever we have negative exponents, instead of having extra zeros and moving to the right, negative exponents mean that we're dealing with a decimal. So this -7 means we're going to take our decimal and move it to the left. And when that happens, when we have to move to the left, we move 1 decimal place to get past whatever number is here. And there will always be a number here if it's in proper scientific notation. But then we still have 6 more places to move. So 1, 2, 3, 4, 5, 6. And I'm going to fill in all these places where there isn't anything with zeros. So now I have 6 zeros between my decimal and the 3. And the negative that's in front of this is just going to make my answer negative. So what am I writing? Negative 0.000000324 is my answer. This should say rewrite in scientific notation because it's already in decimal form. I just did not change the instructions. So there's kind of two parts to scientific notation. One is taking the numbers that we have that aren't zero and figuring out where our decimal place should go. There should always be one number to the left of the decimal and everything else should be to the right. So this should end up being 3.89. The other part to it is figuring out what exponent to put. Part of that comes from counting how many places the decimal is moving. It's moving 1, 2, 3, 4, 5. So we know it's going to be a fifth power. The question is it positive or negative? So the way I remember it is really small numbers like decimals mean that this is a negative exponent, whereas like b, where we have a really big number, that exponent would be positive. The other way, though, is that if we take a small number like 0.0000389 and we make it bigger, we actually subtract however many decimal places we move, and that's how we get -5, which is backwards in the way that makes sense in our head. You would think that if you made the number bigger, it would add exponents, but that's not the way it's working. So, we can internalize that and just remember that, oh, it's backwards from the way that I think it should be. So on B, this is going to be -6.54 because we want one number to the left of the decimal place. And then we're going to see how many places we need to move this. 1, 2, 3, 4, 5, 6, 7, 8. And because this is a big number, I get the 8th power, the positive 8th power. And that should make sense after you look at this, that if I do 3.89 and I times it by 10 to the -5th, which is a decimal, I should get a decimal. If I have 6.54 and I times it by 10 to the 8th, which is a really, really big number, I get a really, really big number. Now, one of the reasons that scientific notation is so great is that we can actually pretty easily multiply, divide, and use powers in scientific notation without having to use a calculator and without having to change it to decimal form to actually do the math part of it. So we're going to use our exponent rules that we talked about in this chapter, as well as the idea that I can do multiplication in any order. Even though these multiplication symbols look different, everything here is being multiplied together. So we're allowed to say, well, let me do the 5 times 7 together first, and then let me do 10 cubed times 10 to the -8. Our exponent rules say that if I multiply together two things with the same base, which is 10, I just need to add their exponents together. So this is 35 times 10 to the -5th. This is not proper scientific notation. I want to change it so that it's 3.5. Whenever I move the decimal over from the 35 to make it 3.5, I've just made this number smaller, 35 to 3.5. That's smaller, so it adds 1 to my exponent. -5 plus 1 gives me -4. I can confirm that that's really the way that works by writing it in decimal form. I can actually write it in decimal form from the 35 times 10 to the -5th if I want to, because I just would move the decimal over 5 places and get 0.0035. And this confirms that we really need a -4, because if I try to put this back in scientific notation, I would move it 4 places to get it in between the 3 and the 5. So that kind of proves that idea that we went from a bigger number to a smaller number, so it added to our exponent. On B, we're going to do the same thing. Our multiplication is a little bit more complicated here. We would probably want to come out to the side and work out what this is the good old-fashioned way. We might not be very happy about it, but that's too bad. So it's 432. We need 2 decimal places because there's 1 from each number. So this is 4.32, and it's negative because the first one was negative. 10 to the -2 and 10 to the -5th, we add their exponents and get 10 to the -7th. We check to see if this is in proper scientific notation, and it is because the 4 is on the left side. Then we figure out what this is in regular decimal notation because it asked us to in the instructions. So we're going to move to the left 7, which means it needs to go one place for the 4 and then have 6 zeros. So 1, 2, 3, 4, 5, 6, and then 4, 3, 2, and it's negative. Dividing is going to work pretty similarly. I'm going to do 1.8 divided by 6. I'm going to choose to do that part first. If I don't know what 1.8 divided by 6 is, I could always come over here and do long division and say that I move my decimal place up. 6 doesn't go into 1, but it will go into 18 3 times, and that means that this is 0.3. The other way to do that is to say I know that 18 divided by 6 is 3, so it must be a decimal, and then to guess that it's 0.3 and then check and make sure you're right. So this is 0.3 times 10. Now if this is on top and this is on bottom, we subtract those exponents. So we want to do -3 minus -3, which is really -3 plus 3, so our exponent is 0. Well, if you remember that 10 to the 0 is really just like having 1, then really easily we know our decimal form for this is 0.3. The question though is, what is 0.3 in scientific notation? Because scientific notation says there needs to be one number to the left of the decimal. So we need to move this decimal over. We need to go from 0.3 to regular 3. I made my number bigger, and so that's going to subtract 1 from my exponent. And if I look up here and think about moving this decimal and how we talked about negative exponents mean decimals instead of big numbers, then that should make sense. On part B, we've got 11/4 to figure out. 11 over 4, we can come over here and we can do long division to figure out what that is. Or we can say 11/4 is 2 3/4, and that would make that be 2.75. So it's important to remember that you can always go back and do things with long division or relatively long multiplication and get the answer that way. But sometimes we can do it in our head just as easily. So what we want to do here with our exponents is subtract them. So 7 minus a -1 is really 7 plus 1, which is 8. We want to check and see if we're in proper scientific notation with one number to the left of the decimal, and we are. And then we want to write this in decimal form. So we're moving the decimal to the right 8 places. That's 2 to get past 75, and then 6 zeros. So 275, 1, 2, 3, 4, 5, 6. The final thing that is related to these exponent rules we've been learning is that we could take our scientific notation number and raise it to a power and use our exponent rules to help us do that more easily. If I have 5 times 10 to the 4th power, this is multiplication inside, so I can give both things the 3rd power and then simplify and see what I get. So 5 to the 3rd power is 5 times 5 times 5, which is 125. 10 to the 4th power, when I raise it to the cubed, that multiplies my exponents together, and I get 10 to the 12th. This is not in proper scientific notation because we want it to be 1.25. I took 125 and made it smaller by 2 places. I made it smaller, so that adds. By 2 places means I add 2 to my exponent. So this is scientific notation, and then my decimal form is 125 and then 12 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It is helpful to put, I think at least, your teacher may disagree, I think it's helpful to put the commas so that then if somebody else is looking at this, it's easier to tell what number you have if the commas are there versus just having, being forced to count how many zeros there are. Same thing happens on B, that we're going to give everything inside the 6th power. Now keep in mind, if I make -1 go to the 6th power, that I have 6 negatives, they pair up and cancel each other out, which means that I just have +1. Then I multiply -3 and 6 together and get -18. That is in proper scientific notation because here's my decimal and there's one number to the left of my decimal. And what I want to do is write this in decimal form so it moves once to get past 1 and then needs 17 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And at this point, you should be like, oh yeah, I would really rather write this number in scientific notation than write it out in decimal form like it asked me to. So that's the idea behind scientific notation, why we use it, why it's helpful, and then actually how to use it to be able to come up with answers like that. So that's 8.4, scientific notation.